YouTube. So good morning, good afternoon, good evening, depends on where you are in the world. So today we have the pleasure here to have a Professor Zainalabedin Navabi from University of Tehran to talk about a RISC-V based processor, paper pencil RTL design and implementation. But before giving the floor to Professor Zain, just some few announcements. So if you lost the talks that are being done since 2020, they are all available in this YouTube channel. So you have about 150 talks available there. They're not here in this YouTube channel. So with fantastic speakers that you can see by yourself. Then the CASS flagship conference in Region 9, Alaska's Latin American Symposium Sequencing System. That is the international conference of CASS in Region 9. So next one will be close to my university. So in the city of Bento Gonçalves, that is just 120 kilometers from Porto Alegre, the most traditional wine region in Brazil. So I hope to see you all there next year. And the call for paper deadline is beginning of September. And the best paper selection, some ones goes to TCAS2, that should appear in the months of the conference in the journal. And during the conference, there is an additional selection to invite papers to a special issue in TCAS1, so extended versions of the papers. And in 2026, LASCAS will be in Peru, in the beautiful city of Arequipa, so always by the end of February. So if you are in the North Hemisphere, it's a good time because it's summertime here in South America. And 2027 to go to Panama City, so another nice location. And there is also as you know, the SBCCI that is also sponsored by CASS, that is organized in Brazil each year in a different location. So this year it's going to João Pessoa in the northeast of the country. And next year we are going to return after 25 years to Manaus to do a next edition of the Chip in the Jungle. So then you have plenty of time to prepare your papers for this very special edition of the conference. I don't have the flyer here, but I will announce soon. Also next year, in the end of April, we are going to have the first Latin conference on IoT. So it's a flagship conference of the IEEE IoT technical community. And this year, CASS is celebrating 75 years. So there is an interesting promotion. So if you are not a member of CASS yet or never been member of CASS, you have a first year of CASS membership for free. This is available for students and also for professionals. And the IEEE student membership is $14. So it's a great opportunity to become CASS member. But today we are here to attend this very interesting talk by Professor Zain Navabi. So Professor Zain Navabi is an adjunct professor. He just finished his work as professor at the Worcester Polytechnic Institute in USA, and he's professor of electrical and computer engineering at the University of Tehran. Is the author of several textbooks and computer-based training on VHDL, Verilog, and related tools and environments. Dr. Navabi's involvement with hardware description language begins in '76 when he started formal definition of a range transfer level HDL and development of a simulator for it. In '81, he completed the development of a synthesis tool for that same HDL. The synthesis tool generates MOS layout from an RTL description. Since 81, Dr. Navabi has been involved in design, definition, and implementation of hardware description language and design methodologies. His work on HDL has continued to language used today for system-level design and modeling and language-based design space exploration methodologies. New domain-specific language and methodologies for AI and machine learning are part of his ongoing work. So thank you very much, Professor Navabi, to accept our invitation. And the floor is with you to start your talk.
Thank you very much for the introduction. And my presentation today is a RISC-V based processor, paper and pencil RT level design and implementation. Let me tell you what it is this about. This is a project that started several years back, and that was supervised by myself and Dr. Paolo Prinetto from Polytechnico di Torino in Italy. And the whole thing is a complete RTL design from the scratch of a RISC-V based machine. Okay, so let's start with the RISC-V based machine and start describing it here. Next slide, please. All right, I'll talk about the processor and then RISC-V processor. This is the outline, and then the processor, we are calling it off top, which is the RISC-V processor, our version of RISC-V. And then I will go through a step-by-step paper and pencil design of this processor. Once this is done, I will cover the interrupt handling part of it, and then show you the simulation and synthesis process, how the hardware description has been done, and how the whole thing has been simulated and synthesized. The next slide shows a processor. What is a processor? A processor, this was supposed to be animated, but since we were not able to get the the PowerPoint uploaded, we are doing it over the PDF files, but it's okay anyway. Anyway, what the processor does is that it reaches out to the memory, it grabs an instruction, looks at the instruction, and decides what kind of operation it's supposed to be doing. And once the instruction is decoded, then it performs the operation of the instruction. For the pointing of the instruction in the memory, it is the register that is called the program counter. For getting the data from the memory, it's a memory data register, and for putting an address into the memory is the memory address register. All the accumulation and all the operations are done in the accumulator or in a register file. Okay. All the tasks are broken into individual instructions. Processors are like Intel processor, AMD processor, ARM processor, and RISC-V, which is the processor that we will be designing here. Next slide. A processing system works like this. There is a bus in the middle, and then there is the processor with its control and data parts on the left-hand side. There is the connection between the processor through the address bus to the shared bus, and then there is the data bus that goes back and forth between the processor and everything to the right-hand side. Everything to the right-hand side is a memory block consisting of an SRAM, static RAM, DRAM, and other form of memory like flash memory and all of that. And then we also have memory mapped IO devices or memory mapped accelerators, meaning that everything else that the processor works with look like memory locations as far as the processor is concerned. What the processor does is reaches out to the memory, brings an instruction through the bus into the processor instruction register, and then the controller looks at that and decides what kind of instruction it is and what it's supposed to be performing. Next slide. Okay. What are the instructions? Instructions are like instruction begin with a fetch. Fetch means go out to the memory, fetch an instruction, bring in an instruction and look at it. And then it's decoded. Once it's decoded, then it's decided what it is. Then execution is done. For example, arithmetic operations, logical operations, shift operations, jump and branch instructions or operations. These are the kind of instructions that the processor performs. Then we have memory access instruction, load and store. And then we have register write back, meaning that the operations like, for example, arithmetic or add and subtract operations are written back into the register file. Mainly the RISC machines have a large register file that contains all the data, and we go out to the register file, we bring in the data from the register file, perform the operation, write it back into the register file. Next slide. All right, let's talk about the RISC processor itself. RISC-V is an open, royalty-free ISA instruction set architecture, meaning that the instructions are available, the format of the instructions are available, it is available to everyone. Everyone can take that and implement their own hardware. Okay, it was developed at the University of California in Berkeley, and then there are RISC-V. There are variations of RISC-V, and it's used for microcontrollers, for small tasks like microcontrollers, or large tasks for like supercomputers and all that. There are several versions of it. For example, a 32-bit, a 64-bit, and a 128-bit. RISC-V has machine mode, user mode, supervisor mode for various security and for or for simple architecture like microcontrollers. RISC-V offers integer, floating point, atomic operations, and more extensions are also available. There are security features and other extensions of RISC-V available. And there is a growing community of RISC-V researchers, software developers, hardware developers, security work people, and so on. And so RISC-V is growing, and it's good to be able to have your own RISC-V or do your research on various aspects of it. Next slide, please. All right, these are the extensions of RISC-V, and the two boxes that are dotted there are the ones we have implemented. We have implemented RV32I, which is the base integer instruction, the 32-bit one, and also we have added the integer multiplication and division to it as well. Next slide. All right. These are various instructions that we are handling. For example, we do arithmetic operation. For example, add is an arithmetic operation. Shift is an arithmetic is a shift operation. Logical operation like and or, all of those are handled. What is shown below is the base instruction, and what's shown there in blue are the multiplication and division operations. And we also have multiplication, and all of those instructions that I'm listing on the left-hand side are part of the base integer instructions, and also the multiplication and division are handled here as well. Next one. All right. When I talk about operands, I talk about operands in three ways. One is an instruction opcode as its operand by itself. Okay, that's usually referred to as immediate operand. Or an instruction has an address into the register file. The heart of the whole thing, the processor, is the register file where the currently working data are stored in there. And so it points to the register file and takes an operand from that, and then a pointer from that, and that pointer in the memory grabs the operand. That's the second one. The third way you can access an instruction, an operand, is to take the opcode, take the address into the register file. This is called the register addressing. So I have immediate addressing, indirect addressing for load and store operations, and register addressing means that the data is in the register file. Next slide. These are the types of instructions that we have in RISC-V. Let's look at those. We have register instructions. There is an opcode, there is a source register, there is a second source register, and there is a destination register. These are 5-bit addresses to the register file. The register file has 32 32-bit words in it, and therefore the RD, which is the destination register, RS, which is the source 1 register, RS2, which is the source 2 register, these are all addresses, 5-bit addresses into the register file. For example, adding means that let's take register RS1, register RS2, add the two together and put the result in RD, which is register destination register. Then we have I-type instructions. I-type instructions are immediate type instructions. Store, which is load and store, storing into the memory or storing from the memory into the register file. Then we have branch instructions, then we have upper immediate instructions, and we have jump instructions. Next one. All right, let's talk about hardware design of TOP or the RISC-V that we have implemented. Like I said, we have the RV32IM. This is the version that we are starting with, which is the one that I'm presenting over here. It has unprivileged mode. It has the machine mode as well. Now we have other versions, which is 32IMF, which is floating point privilege, user, and debug mode. Those have been implemented, but the one I'm discussing today is the starting version, which is the one on the left-hand side. Just a note on the name of the processor. Aftab in Persian means sunlight, and it is a fine Tehran Turin architecture being, and this is the name we've chosen since this is the work that started between University of Tehran and Polytechnic Torino in Turin, Italy. All right, next one. All right. So we want to design the hardware. How do we start? We go read the manual. We find out, okay, the manual says there is a register file. There is a large register file, 32-bit registers, and 32 of them. So we decide that, okay, we do need that register file. Well, it also needs an ALU because there are operations like add and subtract and all that. So we decide that, yes, there is an ALU needed. Obviously, there's a program counter needed, meaning that there is a program counter that points to the memory, and we look up data from the memory. We look up instructions from the memory, and Then we need an instruction register. That instruction register is what comes out from the memory, and the instruction is loaded there. Then we have memory interfaces, and we have a controller. We have a register bank where the status and things are saved there. So we read the manual and we get the general picture like what I'm showing over here. And you see the memory is at the bottom, and the size of the memory and everything is available from the manual. Okay, so let's go on to the next slide. Now we say, fine, we got what we wanted, or we got what we learned from the manual, which is the instruction set, which is the basic registers and the memory interface and all of that. So we did get something from it. Now we have to do the paper and pencil design of the processor. Let's get started with that. Next one. All right. So we start with this. We say, well, let's come up with a simple data path, just a little bit more elaborate than the one that we get from the manual. Okay, we start with the data path, something like what is shown on the left-hand side. There is a register file, there is an ALU. The register file has two output ports. The output ports go into the ALU. The output ports go into some address units so that they can be addressing the memory for reading and writing. And then we have two read memory, write memory interfaces. See, this is the data path, just a little bit more towards the way we are doing it than what we came up from the manual. And also there's a program counter. In front of the program counter there is the address unit. The yellow one is the program counter, the address unit, and then there's the instruction register. That notice that the data bus comes in and goes into the instruction register. And also the data bus comes in and goes into the area for the register file and all that. So that's our starting data path. On the left-hand side, you see the starting controller. Like I showed you in a previous slide, there is this data path here, and there's this controller there, that the controller tells the data path what is supposed to be happening. Our starting controller is that, okay, let's fetch an instruction. Let's look at the instruction, and then if it's execute operation like AND and OR, let's do it there. If it's a memory access, let's go into several states for doing that. So we start with this, and then incrementally we add our registers into the data path, and our control signals or control states into the controller until we have a complete data path and controller of the machine. So let's get started with that with the next slide. All right. All through this presentation, you see this handwritten sketches, which I'm showing on the right-hand side. Actually, these handwritten sketches are exactly the way we did the work. We put this on paper, and this is exactly what I'm trying to show here, that when you want to design the hardware, you have to start with handwritten sketches, paperwork, and so on. So we started with fetch, and we said that, okay, fetching is the part that we go to the memory, get an instruction, and decode it. And for that, we decided, okay, we need an ADR, address register, and we need a program counter that multiplexes into the address bus. And then we have this unit on the right-hand side, which is a memory interface unit. From there, we are taking data, and it goes into the instruction register. So that's the fetch sketch that we came up first. And then in the next slide, next slide, please. In the next slide, that sketch goes to the students who are doing the work, and they decide on the control signal. Notice the difference between this and the previous slide is that here you have control signals. For example, the address register has a load address register. The multiplexers have two signals for selecting the upper or the lower input of it. And then control signals are defined here. Just incrementally, this is just one step closer to the actual hardware. Now, once we have verified this, then the next slide. The next slide, please. The next slide, the visual drawing of that same part of hardware is done, and then we go into the control states, okay? We go into the control states, and then we decide on the control signals that are issued in each state. Notice that, for example, in the fetch state, the increment for PC is issued. That means the program counter has to be incremented by 4, or going into boundary of 4 bytes, and then the other control signals are issued, and then we go into the next state, which is getting the instruction. In that instruction, in that state, we are waiting for the data to come from the memory into that DARU, which is, we call it DARU, which is the memory interface, and then we will take that and put it into the instruction register, as you are seeing it over there. So in this slide, in the third part, after the initial sketch and after the decision on the control signal, which was the second slide, the third one is telling you, okay, these are the control signals. And then what we do next is, next slide, please. There we go. We say, okay, fine. So far, what we have done is we have taken care of the fetch operation. Okay, the fetch operation, which is just the first thing before we do any instruction. Now, the yellow parts are showing the parts that are involved in fetching. Okay, notice the DARU part, which is the memory interface, and it has the buses that go out and the buses that come into the processor. Very good, thank you. And then you see that there are other registers like the program counter, address register, and all of those. So this is the part that is done, and it's yellowed, meaning that fetch involves all of these. For each one of these components, as we do it, we develop the VHDL description, which is on the left-hand side. So, for example, the left-hand side is showing the a register which is instantiated there that takes care of the instruction register, the address register, and the program counter. And then there are other components there, like the multiplexers, the other components there that are also done. We have also done the VHDL description for all of them. So what happened is, okay, fine. We started with that very, very, very basic data path. We decided fetching requires such and such. So we added those on top of this. Okay, next slide. And then we say, okay, now that we have done the fetch operation, we have to come up with the control states and the control signal. And then we come up with what is yellowed there, indicating that these are the states that we have to add to our complete state machine, or the controller of the processor for completing the fetch. Next one is the load instruction. Okay, then again we do the same thing. Notice the load is, we have already got an instruction in the instruction register. We decode it. We find out that it is a load. And then for that, what we have to do is to reach out to the memory and get the address from the register file, and once the address is obtained from the register file, we go in and get the contents from the memory and then put it into the register file as the destination. Once again, we start with this sketch, with this handwritten sketch with my students, and we say, okay, now here is a register file. We need an adder for completing the address. Then the address goes into ADR address register. And then we say, okay, there are some buses and some logic here and there. This goes into this is the first sketch, and then we go into the next slide. Next slide, okay. Now, the students take that and then turn it into this sketch, which has the same registers involved in the loading, plus the signals that you see, the control signals for the registers and the combinational part and the multiplexers that are involved. Up on top is the load instruction with its opcode and various types of the load instruction, which I'm also showing on the left-hand side. We have load word and other forms of load. Some of them use some immediate addressing for pointing to the register file. And once again, once this is done, then we verify that. Then the next slide is, okay, now this is the Visio drawing. Then we verify this, work on this, and we come up with the controller part that takes care of the loading. So the next slide shows, okay, on top of this, these are the three states that belong to the loading. So the loading, and then the next slide is continue loading whatever is there, and then we do the loading there. All right, then what happens? The yellow part that you see here are the parts that we just added to the data path because of the load instruction. Okay, and so all of those are there. The previous parts are already there, and we eventually, after going through all these instructions, we will be able to cover the entire thing. Look at the left-hand side. The left-hand side has, again, as we do the new components of the data path, we do the VHDL description for those components with the control signals and all of that. Next slide shows the controller part. The yellow part is what has been added to it, and these are the controller parts that, notice after decode, we go into that yellow area on the left-hand side where the control states taking care of the load are there. Look at the left-hand side of the screen. You see the VHDL description. That's a partial code of the controller taking care of the load operation. Next slide. This is done. Then we go into the store operation. Okay. Once again, this is the hand-drawn sketch of the store. We work on this with the students, and then we say, well, we need such and such registers. This is a there is an adder there. There is a again, some of the registers of the previous one, and then it interfaces with DAWU, DAWU, which is the interface for writing into the memory. Remember, we said that load is reading from the memory, putting it into register file. Store is reading from the register file, putting it into the memory. That sketch is then handled by students. They go in and take the next slide, which is the control signals. Now, these are all the original drawings. Everything we did on these papers, we took the papers, and this presentation is based on those paper. Now notice the control signals are there and the various store operations are handled by the control signals and all that. Once we verify that, the next one is, let's go on to the next one. Okay, this one, the Visio drawing, and then on top of that, we do the control states that handle the store operation. Up on top, you have the opcode, or the actually instruction for a store, the format of the instruction for a store. Then in the middle is the data path for a store, and then at the bottom, what you are seeing is the hand-drawn states that handle the store operation. Okay, once this is done, then we take the controller and the data path, overlay it on top of the existing data path and controller. So let's look at the next slide. There we go. The yellow parts are the new parts that have been taken care of by the store instruction. On the left-hand side, again, we have the components that are new for the store instruction, and the VHDL description is there. As we are doing these, we are also doing the VHDL description for all of them. And then the next slide shows the controller part that has been added to the controller because of this store instruction. And then again, notice the yellow area is the part that has just been taken care of, and the states that are handling this store operation. Eventually, after going through all of these instructions, we will be able to cover the entire controller. I'm not going to go through all of them, but I'll do a few more. On the left-hand side, these are the controller states, the VHDL description for the controller states handling the store operation. The next slide. Okay, let's do the shift instructions. Okay, the shift instruction is, again, the opcode is there. This is a sketch, the hand-drawn thing. And then we have the shift, the number of shifts, and we have what is being shifted, which is forms the two sources of shift. And then what the result of the shift will be written back into the register file. Notice that the register file is a two-port memory, or is a dual-port register. Then it goes into the BSU, which is barrel shifter unit, and the proper number of shifts is given to it and goes back into the register file. This is a sketch. We talk about this with the students, and then they go into the next slide where every component is better drawn and control signals are decided based on the types of the shift operation that you see on the left. The various control signals are decided. And then the next slide says, okay, this is the Visio file, and now let's go into the various states that handle this shift and the control signals for handling this shift. Next slide shows the control signals on the left-hand side, hand-drawn. And once again, these are the original drawings, the original things that we had from the time that we designed the whole processor. The next slide is, let's put the shift overlaid on top of the existing or incremental data path, and now the yellow part is the new part that is handling the shift. On the left-hand side, you see the barrel shifter VHDL description. Okay, so as parts are being added, the VHDL description is being added, and then the controller part of it. So the controller, we are already showing the parts that have been taken care of. And then now the yellow part is the shift operation that, again, on the left-hand side, the VHDL description for the shift state, issuing the proper shift signals. Next slide. I will do a few more of these and then jump to the complete processor. This is the logical operations and the LLU, which is the logic unit, handling and or and all that. Notice that the instruction, there are two types of the logical operation. One uses immediate, one uses RS1, which is source 1 and source 2, and the destination itself. And then those two are used into the logic unit. The logic unit output is taken back and written back into the register file. Let's look at the next slide. Okay, this is the sketch, but now we have the control signals based on the instructions shown on the left-hand side, and or XOR and immediate, or immediate and XOR immediate, and the proper control signals are issued there. Okay, the next slide shows the visual file plus the control signals, and then the next slide shows the next slide, please. The next slide. Okay, I guess let's go back. One more. There we go. Okay. So the state on the left-hand side shows the logical state, which is part of the controller, and then the signals that are issued there. Okay, we go on to the next slide. Now that we have the data path and the controller, we again overlay the logical part on top of this, and then the new components which we haven't taken care of. The VHDL is shown on the left-hand side, like LLU, which is the logical unit. Okay, then we go into the next slide, which shows the controller, and look down below. The logical is the new slide, is the new state that we are taking care of, and then the VHDL code on the left-hand side, which is the part of the state machine that takes care of the logical state, logical instructions. Okay, let's do a few more of these, and I will go basically quickly through all of these. Next slide, please. These are the conditional jump branch instruction, and this is a fairly complex instruction. The condition uses a comparator, so obviously we haven't done the comparator before, and therefore we need a comparator. And then the comparator will be deciding whether the two ports or the two operands are one is greater, less than, or whatever. And based on that, we will be loading the program counter based on the condition of the branch and jump. Next instruction, next slide shows the hand round with the control signal for the various branch instructions. And then next slide is the Visio file for that. This is actually a very complex instruction, and many signals involved, many new components involved, and so on. And so we had to go back and forth several times before we complete the conditional branch instruction. Next slide shows the overlay of whatever new parts of hardware, new parts of data path that we have decided. I'm showing the comparator on the left-hand side because that wasn't involved in other instructions. And then we have the yellow part, which are the parts involved in handling the conditional branch. Let's go on to the next one. That shows the control state, and then on the left-hand side shows the control signals issued in this state. Next one, please. This one is multiply and divide, basically the same thing. And then we have a sequential arithmetic unit, which actually does the multiply and divide unit, and it has a start, it has an end, and then we take the two operands from the register file, do the multiplication or the division, and then put it back into the register file. Next slide shows the hand-drawn sketch with the control signals and everything that everything that is needed for the handling of multiply and divide. Again, various forms of multiply and divide are shown on the left-hand side. Next one. This is the Visio drawing, and with the proper control signals. And then the next slide shows the overlay of the data path on top of the existing data path. The yellow parts are new, and the rest of those are the ones that have already been taken care of. Notice that incrementally we have added, and most of the parts have already been handled. The next one. Multiply and divide, there are two states handling that, and the left-hand side shows the control states for all of those. The next slide, please. I'm not going to do this in detail. This is add and subtract. Next slide. Okay, that's again the control signals, various types of add and subtract. The next one. That's the Visio drawing plus the control signals handling the add and subtract instructions. Next one. Okay, overlaying it on top of the existing. You see the new yellow parts. The ASU is the add and subtract unit that is taking care of these two operations. On the left-hand side, I have the adder subtractor VHDL description. Next one. And then these are the control states that take care of the add and subtract operations. Next one. All right. We are done with the instructions, and then we will go fairly quickly through the rest of it. In addition, I've been showing you a DARU and a DAWU. DARU is a data adjustment read unit. DAWU is data adjustment write unit. Data adjustment meaning that the registers inside the processor are 32 bits. But then data writing and data reading to the memory is byte oriented, and therefore you have to come up with the individual, you have to come up with a hardware unit that will take the 32-bit and break it down into four bytes for writing or reading. And then next slide, we did the same thing for DARU and DAWU. This is the data path. And notice the controller. This is a sketch of the data path and controller. Then we worked on this. This is a complete data, a complete sequential part. Next slide. And then this is how we came up with that unit just by itself. Notice that there are 4 registers there for breaking the 32-bit operand going into the memory, and that's the state machine for it. Next one. All right, so we have actually shown the data path and all of the components that are there. The processor also has interrupt handling. I'll be done in 3 more minutes. Interrupt handling, and let's talk about that a little bit briefly. Next slide. The interrupt handling hardware takes care of the various devices that need to interrupt the processor. Actually, the interrupt handling part of the processor took about the same time as the rest of the processor. That's a very complex part of the processor. And there is a interrupt controller divided into PLIC and CLINT. That we are not talking about that. We are only saying that there are devices that interrupt the processor, and the processor has to take care of the interrupts. Next slide. Interrupts are software interrupts, timer interrupts, external interrupts. Exceptions are things that happen inside the processor, like, for example, divide by 0. They create exceptions, and then the processor has to take care of that. How does the processor take care of that? Next slide. Okay, the processor handles the yellow part is the part that we have added for the interrupt part. The processor takes the interrupt, finds out the source of the interrupt. Based on that, it goes into a memory location where the part of the processor for part of the register for identifying the interrupt, and all of those are stored, and then we'll do the controller. So everything at the bottom in the yellow part is what handles the interrupt. Like I said, I'm not getting into the details of that, just showing you the controller. Next slide. Okay. All around is the controller. When an interrupt occurs, then the processor is reading reads the interrupt, finds out the source, stores the program counter, activates the interrupt service routine, and then goes and does the service for the interrupt. Next slide. All right. We are done with the processor. This is the way we did the complete design and the VHDL description and all that. And then when that was done, then we do the simulation and synthesis. Next slide. On the right-hand side, you have the software. Then you have the column for the hardware. Then we have the verification of it. The software, we use GCC compiler, and then the binary file is generated. Binary file is generated and tests the FPGA implementation of the processor and the ASIC implementation. Also, pre and post synthesis verification is done based on the pre-synthesis RTL description, the VHDL description of which I was showing, and the gate level netlist. And then on the left-hand side, we are showing the abstract verification. Actually, we developed a instruction set simulator in System C for the processor, and we are verifying that with the RTL description as well. Next slide. This is a very simple factorial calculation that compiles into what you are seeing on the right-hand side, and then that is loaded into the memory. Next slide. And then this is model simulation of the memory, and eventually calculating the factorial for a number for a data that is entered. The next slide. This is the waveform coming out of the model simulator, and notice that we are actually looking at the memory and the register file and all that, and seeing that this indeed does the proper calculation. Just a very simple test case. Next slide. This is the FPGA implementation without the interrupt and with the interrupt, and the areas showing there in darker blue, those are the parts of the FPGA that were used. All the data of the Cyclone 4, number of registers and everything is indicated. Just because we are in South America, the FPGA implementation with interrupt has the shape of map of South America in a way. Okay, next slide. Completed task or layout generation, ISS, instruction set simulator, memory protection, security, floating point, user mode, debug mode, power bank annotation, layout, and SoC environment that we have developed based on this RISC-V for biomedical applications. Next slide. Conclusions, we have a complete processor done. We have shown the necessary steps for doing the design. This is a work that myself and Paolo Pirinello directed, and our emails are right on the right-hand side. All the code is available, manuals, materials, lecture materials, everything that is available, we will share with whoever is interested. We have also done the system C, the Verilog file, the Verilog description, also the VHDL description. The next slide. Okay, I thank you for your participation. And this is a fort in Western Iran, going back 1800 years. Thank you so much for your presentation. We have a few minutes for questions, perhaps.
Okay, thank you very much, Navabi. Very nice and didactic talk. So there was one question here from Aurelio Villanueva from Universidade Nacional de Engenharia from Peru. And
Okay.
was asking the gift hub direction, but it's already included in your slide. And I think that also Nosrati is including here in the chat channel. So thank you. Then I have another question from Luis Duarte from here, from Porto Alegre. From what I have learned, would learning be much more efficient if you drew the processor sequence by hand, trying to reproduce the logic?
From what I learned, would learning be much more efficient if we drew the processor circuit by hand, paper and pencil, trying to reproduce the logic? Well, let me say something that I also had in conclusion. A lot of people, because of the hardware description languages and all that, they think that when you are designing something complex like this, you have to go down you have to start with the hardware description. This is absolutely not possible. My suggestion, or the way that you can do it would be more efficient, as you mentioned, it would be to do paper and pencil, do the paper. Once the paper is done, once you know exactly all the signals, after that, you will do the hardware description. Okay? So describing it in a hardware description language like VHDL or Verilog or any hardware description language would be far more efficient if you do the hand design or the sketches or the paper and pencil design. So the answer to this question, I would say, is yes, it is more efficient. Don't jump at hardware description language so immediately, so quickly.
Okay, thank you. So I'm seeing no more questions. If someone have another question, please do it as soon as possible. So I have one, the layout you presented for each technology you have done the chip.
Let me think. It's an older technology. It's not 45 nanometer, if I'm recalling it correctly, but it is. I think it's a 98 nanometer technology.
It was fabricated, or?
It has been fabricated. Yes, the chip is there, and it has been fabricated, and we are testing it at this point.
Okay, great. So I'm seeing no more questions here in the chat channel. Well, there is another one from José Mauricio Neto. Professor, is it possible to explore this design for multi-core applications considering the necessary amendments?
Sure, exactly. Yes, for multi-core applications, for example, actually, we are using this RISC-V in multi-core SoC applications. For now, we are just doing the SoC framework simulation. But since we have the system C, since we have all the upper level descriptions and all that, when we are developing something, we use the system C descriptions of the processor, we exercise it, we do the design space exploration at the high level, and then the whole system, since we have the RTL description of the whole system, then the individual RTL description will be placed. Let me also say this: the system C description has power back annotated into it, so that when you run the processor, you will be also getting the power consumption clock cycle by clock cycle, okay, which is good for design space exploration. And other works that we have done is we have also come up with a neural network based checker for checking the operation of the processor itself as it's performing.
So I have another question by Professor Altamiro Suzin from the Federal University of Rio Grande do Sul. Thanks for the nice presentation. I like to have a presentation playing with building blocks as we did some time ago. Analyze delay or cycle as they build the architecture.
Analyze delay or cycles.
Yeah, he added another comment. Do students analyze delay or cycle as they build the architecture?
Cycles, yes, but not okay. Cycle and delay, yes, but power comes after that. Okay. So as we are doing it, yes, we do analyze the number of clock cycles, and we also do get some estimate of the timing. But then you don't get the power until you go to technology file. You take the technology file, back annotate them into your gate models, and run power analysis after that. Okay. So clock cycle timing wise, yes, we do get it while we are designing it, but power comes completely after that.
Okay. So there is a question that is mainly for me. Would this video be shared? Yes, all the talks are available in this YouTube channel. If you go there, or if you go here, you can see that there is more than 150 talks. And also, the only observation that when you go to the YouTube channel and you search for past talks, YouTube channel, in each row there is a saturation of number of talks. So you have to go to videos, and also at worst you can do a search, and then you are going to find the recorded talk there of all the talks that were done from 2020 to now. But I have a question here now from Sebastian Samenes from UTEC, Peru. Have you tested to see if the processor created is compatible with any processor already made in RISC-V architecture?
Well, the processor works exactly like a RISC-V. So it is instruction compatible. It is. We are doing the same exact ISA. So yes, it is instruction compatible, but number of clock cycles for the instructions may vary. Also, what I presented here was only the multi-cycle architecture, the pipeline architecture. We have done it, but is not included in this presentation because I believe we first do the multi-cycle. Once we do the multi-cycle, then we pipeline it. But yes, this is compatible with other RISC-V machines. Completely compatible as far as the instructions are concerned.
By the way, there is also another RISC-V processor that was developed by my former student, Rafael Calçada, that is available also in GitHub. The name is Steel, STEEL. So it's another option you have to take a look. And now a question by Fernando Urbano. So he is from University of Valley at Cali, Colombia. What do you think about the application of this processor in post-quantum cryptography?
That is something I don't know about, post-quantum cryptography. I don't know. But I would say if a RISC-V processor is useful for this, definitely our off-top processor is also just like any other RISC-V processor. Let me also say this, that all the VHDL code is available, all the post-synthesis data is available. Also, the presentation slides, the PowerPoint presentation slides have some animation that, Ricardo, if you make those available probably on the YouTube, that would be a little bit more useful.
Okay, so another question from Aurelio Moraes Villanueva from Uni Peru. Please, in which FPGA board have you tested the design?
That was Cyclone. That's the one of the Altera boards that uses Cyclone 4 version something. So if you look at the FPGA slide, you see the name of the process, the FPGA that we are using, Cyclone 4 something.
Okay, so a question from Amihaza Nadi Shagdhari. Do we need the new boards or is AF-Tab compatible with RISC-V boards already available?
Off-top is compatible with RISC-V processors.
Okay, so I see no more questions here in the chat channel. So I would like to thank again Professor Navabi for this very nice talk. So you are talking, maybe some people are curiosity from where you are. So you are talking from your home in Tehran. And so
was that another question or?
No, just acknowledge. So thank you very much. So there is here a comment by Mariam saying the FPGA is the Cyclone 4E.
Okay, good. Thank you. She's one of the PhD students involved in the design.
Yeah. So today we had the participation well, I don't know exactly from all countries because not everybody put his name here on the chat, but considering the ones that I have included in the chat here, we had attendees from USA, Germany, Iran, Colombia, Peru, for sure Brazil, and Belgium. So nice set of countries attend your talk in real time, and many others are going to attend the recorded version that is available, will be available in this YouTube channel. So thank you again for giving this very interesting talk. I hope to see you in person soon, and maybe you can manage to come to Lascas next year. That will be close to Porto Alegre. But there is a late question still, José Augusto dos Santos Lemos. What multiplication and division algorithms were implemented in the architecture?
Okay. A Booth algorithm. Signed, unsigned Booth. Just 1 second. The signed, unsigned Booth. I think signed, unsigned Booth.
Yeah, Marianne is also confirming here the
Okay, good. Thank you, Maria.
good multiplier.
Thanks.
Yeah. There is also here another observation that we have also attendees from Argentina. So thank you very much again. So I hope to see you in person in the near future again. I always remember my wonderful trip to Tehran and to Esfahan and so on a few years ago. This will be always in my memory. Very nice locations.
I have
So
never been to South America. Maybe next year would be my first
yeah,
time.
you have
Argentina
several.
and Brazil.
Yeah. So bye bye. Have a nice weekend.
Thank
Thank
you so
you.
much.
There is also Orlando from Venezuela that was attending. So nice set of countries that were attending real time today. So bye bye. Nice
Thank you
weekend.
so much.
See you soon.
See you soon. Bye bye.
Bye.